Hello everyone, this is Jagiellonian TCS seminar from Krakow. Today our speaker is Ugo Giocanti from our group. He will tell us about what? Graph structure theorem, cycle basis.
Yeah, also.
No Schimon's factorization though.
Oh, I will mention it.
I will mention it. The floor is yours.
Okay, thanks a lot. Thanks for introduction. So in fact, I'm super excited to show this work. So this is super fresh. So this is joint work that we did together with Colin Genier. So Colin, you already met him for those who were there last year. He came to visit our group last spring, so he's now a postdoc in IBS in South Korea. And we started this project when he was there. But so maybe let me give you, before starting talking about cycle basis, a little bit of context. So some weeks, months, let's say, after we started working on this project with Colin, we learned, after exchanging some emails, that there was a concurrent group working on some quite overlapping questions, okay? So namely, Bobby Miraftab, Pat Morin, and Jelena Yuditsky. And from this point, we started to try to make our works disjoint, right? To go in different directions. But still, it turns out that there's a lot of interaction between our two works. So our paper appeared on arXiv like a couple of weeks ago, and their paper appeared just today, this morning on arXiv. So now everything you might have the full picture on the topic if you go on arXiv. And yeah, I will try to make clear how we can use their results, in fact, to improve ours in some specific part. And I will try to make clear what parts intersect, what part are disjoint. Okay. Okay, so yeah, I'll talk about cycle basis. Okay. So yeah, I need first now some very simple basic definition. So let's introduce first notion of sum. So I will call it F2 sum, Z2 sum, whatever. So you take two graphs, so finite graphs. So yeah, by the way, usually I like infinite graphs, but today it will be only finite graphs, right? So take two graphs, and so what I call the sum, the F2 sum, is you take the union, and then you remove every edge which is in the intersection of the two graphs, right, of the two edge sets. So you just keep the symmetric difference. So if you start with this red graph, this blue graph, you can see that they exactly have this path of length 3 in common, right? These are the three common edges. So whenever you do this sum, this F2 sum, this is a graph that you'll obtain, right? Okay, so second simple definition, I will call a graph even whenever all its vertices have even degree. So in an even graph, I can have some isolated vertices, right? Degree 0, it's allowed, and I can have more. And what we'll call now, if I'm given a graph G, and if I look at all its even subgraphs, right? So what we'll call its cycle space, it's a set of all even subgraphs of a graph whenever I equip it with this sum. So it makes it kind of a vector space, right? A Z2 vector space, a very simple one. And yeah, so basic observation to see that it is well defined as vector space is that, yeah, so whenever you take two even subgraph of a graph, if you do the sum, it's still even. It's quite an easy exercise to check, okay? Okay, so first simple remark, so why do we call this graph, this space, the cycle space of a graph G? So in fact, because there is a very simple remark that if you take an even graph, an even subgraph of a graph, either it has no edge, then it's a zero element, right? Or if it has at least one edge, and it has some vertex of degree at least 2, and you can start following a path from this vertex, and at some point you will obtain a cycle, right? Because your graph is finite. So you take a cycle, and now if you take an even graph, an even subgraph, you remove a cycle, you're still left with an even graph, right? That's very easy to see. And if you keep doing so, in fact, you can see that every even graph, you can decompose it, you can obtain it as a sum of edge disjoint cycles, okay? So in other words, in fact, if we look just at the set of cycles of my graph, it generates the cycle space, right? So that's why we call it the cycle space of a graph. So I take all the cycles and I look at whatever is generated by this sum operation, and it gives me the set of all even subgraphs. So now, yeah, from now on, we will really focus today on cycle, and just keep in mind that whenever you do the sum with two cycles, it's not necessarily a cycle anymore, it might be even. But that's basically all. And what I call a cycle basis of a graph G, for simplicity, it will be a set of cycles which are enough to generate all other cycles, or equivalently, all even subgraph of a graph, right? Everything so far is good? Okay, so let's look at a very simple example of a cycle basis. So you take a planar graph. So for simplicity, let's take it to connected, just in order to have the property that every face has its facial boundary, it's a disk, right? That's the only thing that I care here in this example. So take a plane graph, so you draw your planar graph, right, to connected. If you take the set of all facial cycles, so for every face you take like its boundary, right, its facial boundary, it's a cycle, this gives a cycle basis of my graph. So why is it? You take any cycle, so this red one, and you take, so it has, so that Jordan-Cuse theorem, it has two regions, interior, exterior one. You take everything which is in the inside, and you sum for every, you do the sum of all fascial cycles which are hidden inside, right? And if you do it, you can see that you have what? You have two kind of edges that appear in this sum. You have these black edges, so these black edges appear exactly in two different faces, so they will cancel when you do the sum. And then you have these red edges on the boundary, and they appear in exactly one face, so they will remain. And that's a very simple way to see, so then into connected plane graph, all fascial boundaries, right, all fascial cycles, they give a cycle basis. And in fact, so in this example, in this specific example, there is something more that we like a lot with this kind of boundaries. It's not any kind of cycle basis. It's a basis. It's a cycle basis which has a property that it has bounded edge congestion. So what do I mean? I mean that if I take any edge in my whole graph, it appears in at most two faces. So in particular, in at most two face boundaries, right? So more generally, I will define the edge congestion of cycle basis, or more generally as a family of subgraph of a given graph, as a minimum possible case such that every edge of my graph G appears in at most k element of my family. Okay, so this cycle basis, it has edge congestion 2, right? Exactly 2. And so now what we will work on today, so the graph parameters that we will define, is the basis number of a graph. So if I'm given a graph, its basis number, it will be the best edge congestion of a cycle basis of my graph, right? So the minimal possible k, such that my graph admits a cycle basis with edge congestion at most k. Okay, so if we put together everything that we saw so far, so planar graph, so not only two connected, in fact, also just general planar graph, they have basis number at most 2, right? You can just take this and you take it in every block if you want to look at the non-two connected case, right? But you can take like so this set of fascial cycles, and this gives a cycle basis with edge congestion 2. So the planar graph has a basis number at most 2. And in fact, there is a remarkable theorem, so which is really the start of this work on a basis number from MacLane. It's called like MacLane's planarity criterion. It's quite an old theorem for graph theory, and which says that in fact this characterization gives an exact characterization of planarity. So not only every planar graph has basis number at most 2, but in fact if you are given a graph with basis number at most 2, you can find a planar embedding of it. And now, just for curiosity, I'm continuing my poll every time I'm talking about this result. Who here already heard about this MacLane's planarity criterion, already know it? Oh, cool. So yeah, I had 1 in total for the last 2 talks. So okay, so yeah, good. Yeah, so to my mind, it's really like an underrated result. Like, I mean, I don't have the feeling that in graph theory there are that many people who are familiar with MacLane's planarity criterion. Well, it's a super nice algebraic characterization of planarity. Like, we are more familiar usually with Kolatowski, Wagner's theorem, Dutch theorem, but for me it should be a basic as well. It's super nice. Okay, so a bit of history, of context. So yeah, so MacLane didn't talk at all in this whole work about basis number, right? He just proved this result, how easy it is. And in fact, it's Schmeichel in 81 who introduced this parameter, this basis number parameter. And yeah, in an attempt to try, to understand now what does it mean to have bounded basis number more generally, what kind of extension of this kind of theorem we can get. And that's really like the line of work that we followed with Colin in this work. Okay, so let's look at some very basic properties together of basis number. So first, let's start with the good news, the thing that we like a lot with basis number. So the very nice thing is that it behaves super well with any kind of simple topological operation on a graph that you can consider. So you take a graph, you subdivide its edges, right? So you take an edge and you subdivide it. A very simple remark is that it will never change, subdividing edges, the basis number of a graph. And conversely, if you take a graph, you take an edge, and you contract it, it will never make the basis number increase also. So that's a very, very simple remark, a very simple exercise that you can try to do on your own if you have time. So basis number behaves quite well with respect to subdivision, with respect to edge contraction. Also, there are some properties that we like a lot usually when we are working on some graph parameter, which is that also it behaves not so bad with respect with edge addition, vertex addition. So you take a graph, you add any edge or any vertex, and it will only increase by a constant term, so 1 or 2 according to whatever you do, the basis number of a graph, right? And these two inequalities, they are tight. You can check it also. So this is not so hard, these are basic properties. And so now, but now the problem is that there are some very bad news, and typically it's the very reason why we struggle to understand what basis number means for non-planar graph. And yes, so the big bad news is the following, is that it's does not behave well with respect to subgraphs. So it's not a monotone parameter. And by this, I mean that if you take a graph, if you remove edge, the basis number could increase, right? It is not necessarily monotone under edge deletion. So still, okay, we are not that unhappy because, yeah, what we can show is that if you take a graph, if you remove like k, at most k edges, it will only increase in like some constrained way, right, by some log square k term. But already it's not a super good news, but there are even worse. So some super bad news is that whenever you look at the operation now of you removing a vertex, now it can explode. So if you give me any k, an integer, I can give you a graph. I can find you a graph with basis number super low, so 3, but such that if I remove a very precise vertex, now the basis number will be arbitrarily large, so at least k. Okay, and that's really like the main reason why we don't understand really well what happens beyond planarity when studying a basis number. And that's some very, very weird behavior. We are not used, I think, at least for me, usually to consider such parameters. Okay, so what's known? Here's a reminder of MacLane's planarity criterion, which was really like the first motivation to study this basis number. So planar graphs are exactly the one with basis number at most 2. And then, so yeah, I told you it's Schmeichel who really gave it this parameter this name and who started a systematic study on this basis number. And he proved, so first, that there are graphs with arbitrarily large basis number. Okay. And so yeah, I think it was taking 1 minute to talk about this graph because it's quite interesting. So it's not any graph. A simple way to see that a graph has a large basis number is usually to take the well-known construction of graphs with large girths and let's say minimum degree 3 or large average degree. So usually you take this family of graphs and they will have unbounded basis number. And the thing which is quite interesting is that, at least to my knowledge, it's kind of the only source, the only reason that we know so far for a graph to have a large basis number. So I don't mean that all graphs with a large basis number should have a large girth, but what I mean is that if you want to construct all the construction that we know, the interesting one, usually the main reason is that there is some graph up to doing some small modification. We always started with a graph with minimum degree 3 and large girth or large average degree. Okay. So yeah, so this is really quite interesting, and we don't understand. Like it could be super interesting, I think, to find some other construction, but I don't know if there exists or some other flavor. Yeah.
Is this a random construction, or is it the deterministic one?
Any construction that gives you a family of graph with large girth and minimum degree 3. So there are some randomized ones which are quite simple. But there are also some others. There are the expanders, the Ramanujan expanders. In fact, we like them quite a lot because they give KD graphs, which have unbounded play. They give cubic graphs also, which have unbounded. So there are many of these constructions. You take your favorite one, and it works. But that's kind of the only source, the only reason that we know so far for graph to have large basis numbers. So that's weird. Okay, so yeah, what Schmeichel proved also is that so cliques, and more generally big cliques, they have bounded basis numbers, so these bonds are tight, and we know all the list of cliques, big cliques having 3, 4 as basis number. And it really highlights, it shows really once again, it illustrates well this non-monotonicity behavior of this basis number. And then, okay, so this one is super funny one for me. So there is this result from Friedman and Hastings. So they prove the general upper bound on basis number, so in terms of the number of vertices, n, of a graph. So in fact, it's always at most log square n, up to some constant multiplicative factor. And why is it funny? So because, yeah, okay, so this result, we heard about it thanks to Bobby Miraftab, Pat Morin, and Jelena Yuditsky. And in fact, it's quite hard to find it, at least if you're a graph theorist in the literature, because they did it in a paper where, the goal was to apply it in quantum error correcting code. So they don't use at all the word basis numbers. They don't use all the keywords that you could. So it's quite hard to find, and yeah, that's quite fun. And yeah, and there is a conjecture, in fact, that maybe this log square n, it could be reduced, it might be reduced to a log n, but we don't know so far. So it's somewhere between the best bound between log n, we have some construction giving log n, this large girth thing, and log square n, it's somewhere between. So then, yeah, if we want to, to kind of look at generalization of this MacLane's result, so yeah, first very natural generalization of planarity is to look at, okay, now what when we look at graphs embeddable in some surface of bounded genus. So in the case of orientable surface of bounded genus, Schmeichel proves the following. So it's very simple to prove. He proves that every graph that you can draw in surface, in an orientable surface of genus G, so torus with G holes, you can bound its basis number, it's at most 2G plus 2. And quite recently, last year, there is Florian Lehner and Bobby Miraftab. They proved, in fact, that this bound in any kind of surface, not only orientable, non-orientable also, it could be improved to log square G. Okay, so you have again this log square that appears somewhere. And again, it's open whether like the log square is optimal or it could be log G. We don't know, but we know that it's at least log G. We have some construction with log G. And moreover, they prove that if you look at toroidal graphs, so graphs that you can draw on the torus, you can prove that the basis number, you can find an upper bound of 3, which is optimal thanks to MacLane's planarity criterion. Okay, and so now when you see all of this, when you see also, sorry for spoilers, the title of the presentation, there's a supernatural generalization of this thing. Is like, the natural question that we have is, okay, what about class of graphs that in general exclude some fixed graph as minor? And that's what our work do, so that's what I will talk to. So, okay, maybe a quick reminder of minors for the one who are not super familiar about it. So when I say a minor of a graph, it's topological notion of containment. So you're given two graphs, graph G and the smallest graph H. I will say that H, you can find it as minor in G if you can remove some vertices, remove some edges, okay, obtain it like this. So far it's just definition of subgraph. And moreover, you can contract edge, right? So contract edge, you can select this purple edge, you remove it, you replace it by a vertex, and its neighborhood is a union of the neighborhoods of the two extremities of this edge, right? So you contract this edge, it's a graph that you obtain. If you contract all this purple edge, simultaneously you obtain this graph. So this graph is a minor of this graph, okay? And the very basic observation, I say that it generalizes everything because property of being planar or being embeddable in given surface, it's something which is closed under taking minors, right? So yeah, so usually whenever there are some properties that hold for planar graph, bounded genus graph, we try to understand if they hold more generally for class of graphs that exclude a minor. And so yeah, so that's our main result. So our main result is a positive answer to this question. So it's kind of rough generalization of this MacLane's kind of criterion. So if you fix a graph, any finite graph H, and you look at all graphs that exclude H as a minor, so then in fact you can bound against the basis number of your graph. So that's our main result. Okay, so yeah, and this bound you can express it in some function that I will call f minor on the size of H, okay. And yes, so let me comment a little bit. So yeah, so I will spend most of the time now, from now on the proof of this result. So the proof is quite technical. It uses a lot of machinery, recent tools, more older tool, right? So a lot of stuff. I will not go into details unless you really want, but you don't want, believe me. But I will try to give you at least some key ideas. But before this, yeah, let me maybe comment a little bit on this result. So, okay, so first thing, what if we care about this value of this f minor? So, yeah, so let me mention that, yeah, so first we had an original proof. In our original proof, we had a proof, right, self-contained, where we obtained initially this bound, which is double exponential in t-square. So it's not that far, still already it's something that you can write on paper, so it's good. But yeah, so it's, one could ask, okay, yeah, is it optimal? How can we already find like a polynomial bound, a polynomial upper bound?
So T is the number of vertices of H?
Yeah, sorry, yeah, so T is number of vertices, so yeah, here I wrote it like this. The size of H means size, number of vertices order. And first question that you could have is, okay, what about, is it optimal or not? And in fact, yeah, so the thing which is interesting is that, yeah, so in our proof, almost all of our proof, in fact, it was giving a polynomial bound with like the polynomial upper bound with some very bad degree, except one single step. There was one single step in the proof, and I will show you which step, where we paid a double exponential, like this double exponential dt square. And because of this single step, which was very well localized in our paper, it was the only reason for our bound, our initial upper bound, to be non-polynomial. And it turns out that this result, so this work that I explained from this concurrent work of Miraftab, Morin, and Yuditsky, they tackled this exact case, right? So they gave an answer, they gave a polynomial in this special case, and we will see later what it is. And so taking the result, by applying it in our proof, in this single step, gives now overall the following upper bound. So now we have a polynomial upper bound on the basis number of graphs that exclude a minor. Okay, so yeah, degree is not super nice, but already it's something that you can write, so I mean, I've seen worse. Okay. And yeah, and the thing that we are super happy, okay, so the second consequence of our result, or like a nice consequence, is that in fact, it gives, so it's an if, right? If you exclude some graph as a minor, you have bounded basis number, but we can have some kind of MacLane's like criterion for graphs excluding minor. So it doesn't characterize at all what it does mean for general graphs, general class of graphs to have bounded basis number, but if we focus on the class of monotone class of graph, so monotone class of graph is a class of graph which is closed under taking subgraphs, right? So under removing vertices and edge. Now it gives some kind of criterion, so some exact characterization in the same flavor in some kinds of MacLane theorem of what it does means for monotone class of graphs to exclude some fixed graph as minor. So by this I mean that if you take a monotone class of graph, it has bounded by basis number, so there exists a uniform bound on the upper bound on the basis number of all its elements of the class, if and only if there is a single graph, a fixed graph H, such that everyone in my class exclude this graph H as minor. Okay, and yeah, maybe let me spend 1 minute explaining you how it follows from this main theorem, because it's not very hard. So fix a monotone class of graph C. So if there is a fixed graph, so the reverse iteration is an immediate application of our theorem, right? If there is someone that everyone excludes as minor, you apply our theorem, you get the basis number boundedness. But conversely now, assume that there is a bound on the basis number of everyone in my class of graph, right? So now what I take is I will take the minor closure of C, so the set of all minors of people. So if I take any graph in G, I add also all its minors. And we know that our class, we started from a monotone class of graphs. So this operation of removing vertices, removing edges, I don't need to do them anymore to obtain all minors. So the only thing that I need to do in order to obtain all minors of my people in my class of graphs is to contract edges. And that's one of the only things that we like with basis number, is that I told you already, when you take a graph, you contract an edge, it doesn't make the basis number increase. So take a monotone class of graph, bounded basis number, you take this minor closure, it still has, because of this simple remark, bounded basis number. And so in particular, as we know that there are graphs with arbitrarily large basis number, you take anyone which is not in this class, and this gives you the fixed graph H that now everyone in my original class excluded as minor, right? Okay, so that's more or less what I wanted to say about consequence of this result. So now, bad news. So let me start explaining you, giving you some ideas of how our proof works. And the first bad news for everyone who is familiar at least with this is that it relies heavily on Robertson-Seymour structure theorem. So before going further, I will try to give you some rough ideas, at least, with rough definitions also of Robertson-Seymour structure theorem. So just maybe a rough explanation. So Robertson-Seymour structure theorem, or graph minor structure theorem, GMST, I will say so far from now on. Its result, it's really one of the deepest results I think that we have so far in structural graph theory. Like it's the core result of the theory of graph minor series. And basically it does the following. It says that if you look at all graphs that include a fixed graph H as minor, it gives a way to decompose them in simpler pieces. I will explain what it means in simpler pieces, right? And it gives really like a way to understand the structure, to deeply understand the structure, right? So there are two tools, two ingredients that I will need, that I will give only informal definitions in order to be able to state this Robertson structure theorem. So the first one is notion of 3D composition. So sorry for everyone who is already an expert in 3D composition. But roughly speaking, so 3D composition consists of doing the following. So you take a graph, right? You don't understand this structure very well. And the goal is to try to cut it into simpler pieces, right? And such that these pieces, independently, they have nicer structure. I understand them independently far better. And to glue them together. And the way to glue them together, it will be described by a tree. So there is a tree somewhere that explains me how to glue all my pieces together. So a little bit more formally, if you start from the following graph, for example, a 3D composition can be obtained as following. So you can keep doing the following operation. So you can take two pieces. So you can see that this orange part, this orange section of my graph, it can be obtained by taking this smaller graph, and gluing them. And by gluing them, I mean identifying red with red, green with green, and blue with blue, right? So you identify this guy, and by doing so already you get this orange induced subgraph of your original graph. So let me add a little bit more vocabulary. So whenever I do this gluing, this operation, so these two very small atomic subsets that I will consider, I call them bags. So bags are subset of vertices of my original graph with simpler, individually simpler structures. And the subset that I use and that I identified, it's what I call the adhesion sets, okay, of my decomposition. And if I want now to obtain the remainder of my graph, so you can see that this top vertex, for example, if I want to add it to this previous orange graph, I can just add it by gluing this triangle like this to this bag, right? And every time, in fact, what I can do to obtain the rest of my graph, I can choose a bag that was already present, add a smaller structure, glue it like this, and so far, until I covered every edge and every vertex in my original graph, right? So by doing so, now I obtain what I call a 3D composition. So what's a 3D composition? So more formally, it's this set of bags, right? So these green parts. so these smaller pieces, and there is a tree that explains me in which order, how I connect them together, so, right? So it's a pair with a family of bags and a tree, how to connect them. Okay, so let me add a little bit of vocabulary. So yeah, usually when doing tree decomposition, one of the big challenge is, given a graph, try to find the tree decomposition. So yeah, a case in which we are super happy is whenever our tree decomposition has bounded widths. So what do I mean by bounded widths? I mean that if I can find a bound on the size of each bag, right? So the width of my tree decomposition is the max size of a bag -1 for some historical reasons. But unfortunately, it's not always the case, right? There are graphs like big grids that do not admit such decomposition. And so usually, and that's what we'll do really today, the thing that we are already happy with is if we can find some tree decomposition where the addition value of my tree decomposition is small. So the addition value, by this I mean that it's the maximum size of an addition set. So this means that at each step of my process, right, of gluing, I always identify a small number of people together. And that's really, so the tree decomposition, kind of tree decomposition that we'll consider today, they will all have bounded addition, okay? Bounded addition value. Okay, so now that was the first tool. The second ingredient that I need before stating my this Robertson Seymour structure theorem is notion of almost embeddability. So we already kind of know what it means to be embeddable in a graph, right? So you say that a graph it's embeddable in surface. So yeah, my surface, by the way, that I will consider today, they might be orientable, non-orientable. It doesn't really matter. It's more or less the same reasoning in both, in what I will do. And you take some graphs which are embeddable, so that you can draw without two edges crossing in surface. So you can really think about some just multi-hold torus. And I will say now that I'm almost embeddable if I can obtain my graph. So this almost, it will be parameterized by two parameters, so this A and this B, right? And so if they are small, that really means that I really looks like a graph that I can draw of my surface. So start from a graph, this green graph, embeddable in surface. And I will say that it's almost embeddable, my graph now, if I can obtain it by starting with a graph drawn on my surface and add some kind of decoration. There are two kinds of decorations that I can add. So the first kind of decoration is what I call vortices. So I will not give a formal definition of what it means vortices because we will not really need it, but the picture is quite easy to get. So what means vortices? So these vortices, I can add vortices if I can find some faces, so some disk, I can draw some disk, so this white disk here. And this disk, okay, they must have the property that they should not contain the interior of an edge. That was already present there, right? So they can be tangent to my edge. So in other words, these disks, I have to really draw them in some faces of my previous green graph, right, that I embedded. So there are at most B number of vortices, so B number of disks like this that I can draw. And inside each disk, I can draw some stuff which is non-planar, which is not embeddable also in this surface, we don't know. But it still should kind of have some structured structure. And what does this mean structure? It means more or less that there's a way to draw it with some kind of thickness, which is like parameterized again by this B, and which is circular, like with respect to the order, the circular order induced by the boundary of my disk. Okay, so that's more or less a rough idea. I don't want to say more about vortices because we won't need this more today, at least for what I want to say today. So that's the first kind of decoration. You can add at most B vortices. And then there's the second kind, so this red decoration. This is for apices. Second kind of decoration that you can add to be almost embeddable. So once you have your green plus blue graph, you can also add some red vertices and red edges. And this could be they could have any kind of adjacency, but they should be at most A such vertices, so A such apices that you can add, right? So a graph, it's AB almost embeddable, right? Or almost embeddable is, roughly speaking, you start from a graph that you could draw in your surface of bounded genus, right, that you fix, and then you can add some decoration, so some bounded number of vortices, plus some bounded number of apices, which can have any kind of adjacency with respect to my green and blue graph. That's a rough picture. And so usually we are happy when these two parameters are at least constant or small, right? We consider that it really looks like a graph which is embeddable in surface.
So the apices can be adjacent inside the vortex.
Yeah, they can. It's not okay. It's not apparent. It's a bad example because it's not apparent on the drawing, but they can. Thanks for the question. It's any kind of operation. But in fact, these apices they won't bother us because of the properties that I told you. That if I take a graph and if I add these apices, at most A apices, then it's at most 2A, the increase on my basis number. So it's really not the hard part of our proof. Like, it's very simple to deal with it. We already have everything in it. It's some other issues that makes it harder, the proof. So the raw statement of the grid minor structure theorem of Robertson and Seymour now is the following, is that now if you fix any H, any graph H, and you look at all the possible graphs that exist that exclude H as a minor, right? Then there are some constants, and these constants, they might be quite large, but they only depend on this fixed H, this fixed obstruction that I fixed, and such that now every graph that excludes this given H as minor, you can cut it in simpler pieces. So by cutting, I mean there exists a 3D composition of my graph G with bounded adhesion, small adhesion. So this adhesion is at most K, where K only depends on this H. And moreover, every piece, so I didn't explain what the torso is, but you can really think about bag. Today we will not really need the definition of torso, it's just some small modification of my bag, right? But every torso, when I say torso, you can translate by bag. In this presentation, that will not really matter, even if for the proof we will need torso. So every bag, independently, every torso is almost embeddable in surface of bounded genus. And again, so the genus of my surface only depends on the fixed graph H, as well as these parameters that quantify how I'm almost embeddable in this surface, okay? So that's the rough idea of the graph minor structure theorem. So if you exclude a graph, or equivalently a clique as minor, then you have this structure. You can cut your graph in smaller pieces, and independently, all these pieces, they have this structure. They really look like something that you could draw on surface. Okay, so yeah, let me comment a little bit on these values. It will matter, especially if we care about polynomial bond, the polynomial bond that I mentioned before on basis number. So yeah, so in fact, in the original statement of this graph minor structure theorem, we just knew that there were constants depending on H, but we didn't even have any kind of functional relation, functional upper bound with respect to the number of vertices, the size, the order of H. So except for G, okay, G we already knew from the very original statement that we can choose it to be roughly the size of H square. But K and A, it was not clear at all. And quite recently, there was a huge breakthrough by Maximilian Gorski, Michał Severin, and Sebastian Widerrecht. So Michał presented it to us already last year, by the way. They proved that, in fact, all these parameters, especially this K and A that we didn't know, you can choose them to be polynomial in the size of H. So again, with some large degree, but not that large, like we can write it again. And that was a huge breakthrough, and obviously, I told you that our proof relies on the graph minor structure theorem, so if you want to improve it and to get the polynomial bond, that's the version that you need to use of the graph minor structure theorem. Okay, so that's roughly the statement. So now, okay, so this is a reminder of our main result. So yeah, so now let's try to use this grid minor structure theorem. So there are these two tools that we need to understand how basis number behave with these two objects, so with 3D composition of bounded adhesion and with respect to graph almost embeddable in surface. So these are two different parts of our proof. So the first is really the most technical one, not in terms of size, but more in terms of it relies on some very recent tools, really very recent machinery, and there are many ideas. And the second part, I will not have time to talk a lot about it today, the almost embeddable in surface. It's still quite technical, it's not as easy as what we initially thought. Okay, so let's first focus on the first part. So how does basis number behave with respect to 3D composition of bounded adhesion? So what we would like to prove, so don't read the statement for now, then you can read it, but what we would like ideally to prove in order to be able, if we are naive and in order to be able to use this graph minor structure theorem, would be something like the following. Assume that you're given a graph and that it admits some kind of 3D composition, where each bag, each torso, okay, each part individually has bounded, as small basis number, so basis number at most B, universal constant, and such that moreover, this 3D composition has bounded adhesion. So something we would like to say is that, okay, then I can also bound the basis number of my whole graph, right? Okay, the point is that it's not necessarily true if you just have this hypothesis, and there is a third hypothesis, that's the one that we need in this statement, in order to make it work, which is that in fact you should ask not only every bag, every torso to have bounded basis number individually, but also all their monotone closure, so all their subgraph. And that's the first result, maybe one of the main results, the main tools that we need, and the most technical in terms of proofs in our work, is the existence of a function, more formally. such that if you look at every graph that admits so 3 decomposition, I say it again, bounded adhesion, so adhesion at most case, there is a universal bound on this adhesion, and so that every path, every piece, every torso not only has this basis number B, but also all of their subgraphs, so the monotone closure of all torso also have a bound on the basis number. So then if you have all of these hypotheses, you can conclude that the basis number of your graph is at most some function of your two parameters, so it's bounded. Okay, so that's the first part of proof. So yeah, it's a schematic representation. I don't know how much it helps. And yeah, and the second part, if you want to be happy and to conclude by using the graph minor structure theorem, is the following that we proved, is that if you look at graphs which are almost embeddable in surface of bounded genus, so where you fixed all parameters, A, K, G, all the parameters of this bounded, almost embeddability, right, property, then you can also find a bound on the basis number. And yeah, let me just mention, I will not expand that much on this part again today, but let me just mention why it's not as easy as we thought initially, and it's really because the hardness in this second part, the technicality, it really comes from this non-monotonicity behavior of this basis number. Like, we are super happy if we start from this drawing, for example. On this graph, it's super easy to find a simple bound on the basis number of this graph. But the problem is, if this thing are not real cycle, this blue thing that we glue on, and if this green graph is not connected, and it's really like the non-connected case, it's really the case in which it starts to be harder. Like you have far more interaction and it's hard to analyze how the basis number behaves. So we need some more results in order to prove the second part. So I will not expand on this, I will expand more on the first part. But let me just tell you that yeah, maybe our proof is not optimal, maybe it's overlong, but for now we don't have a simple proof for this part, while we really thought that it could follow from the previous normal results. Okay, yeah, and again, I told you that we can make everything polynomial. So again, there is a single step, and I will explain which one, in these proofs, where we pay in our initial proof the double exponential, but using the result of Miraftab, MacLane, and Uditsky, in fact, we can make these two functions polynomial in all these parameters, okay? Okay, so let's zoom a little bit more on the proof. So in fact, there are 4 main steps, let's say. So the first step is the less technical, I would say. It's the first one. We really had it. It's very natural to get. So the first thing that we do in our proof, so the first thing is to try to prove this result. So now for 3 decomposition of bounded adhesion, how to inherit the property of having bounded basis number. And the very first step, what we do is we take a 3 decomposition, any kind of 3 decomposition, and we try to find some first condition, very natural, which are not as strong as the one that I showed you, but some very natural conditions that could make us able to inherit the property of having bounded basis number. So if everyone in my 3 decomposition has bounded basis number, I want my whole graph to have bounded basis number. And our first step is to find some very weak condition. I will explain why they are super weak. I will state them more formally in a moment. And yeah. And so we obtain a first weak theorem, weak version of the previous theorem. So the second step is a step which is quite interesting. So it's not the most complicated at all in our proof. So it's to prove the previous theorem to deal with 3 decomposition of bounded adhesion in the special case of when the 3 decomposition we look at is a path decomposition. So what does it mean? It means that the tree behind my 3 decomposition is just a path. So my graph, I can decompose it by bags, and this bag, I glue them one after the other, right, along a path structure, and so that between 2 consecutive bags, it has bounded adhesion. There's a small number of people. And so the second step, so the second step is quite essential. So because it was really the step in our original proof where we paid this double exponential. And the reason why we paid this double exponential, it was because it relied on some result from semi-group theory called Schimon's factorization for a theorem. And yeah, so our proof, our initial proof, we kind of like it a lot because it was like, it's not very hard. It's like you use some connectivity abstraction, you represent some paths of decomposition, you encode it in some way as elements of a finite semi-group, and then using this big tool from semi-group theory, you can conclude and get this result. The thing is that it was clearly not optimal. In fact, you can avoid using this Schimon's factorization, this Schimon's factorization theorem. And this is exactly what did Bobby Miraftab, Pat MacLane, and Uditsky. They did, in fact, they proved also this result, this second result for path decomposition of bounded adhesion, but with far better bounds. So that's the paper, the preprint just appeared today on arXiv. And so using these results in the second step, their results, the optimized result with polynomial bounds instead of ours, it makes everything polynomial in everything that comes later. Then there's a third step. So the third step, I think, the most interesting, but also like the most technical. So the third step is now we know that our result for tree decomposition holds whenever we look at past decomposition of bounded adhesion, and is to generalize it to general tree decomposition. And this we can do it. And the reason we can do it, in fact, so the way we do it is we take some work of Mikołaj Bojanczek and Michał Pilipczuk. So it's a work that they use to prove a conjecture of Courcelle. Don't even ask me to state me the conjecture, but yeah, it's something related to MSO and software and logics and all this stuff. And in fact, yeah, so the nice thing is that in their work, they really introduced a lot of very nice structural results, tools to deal with tree decomposition, tree widths, and using this method and extending them. So it's really like reusing all of their ideas, which are quite technical. I will try to give you at least some rough idea of what they do. We can, in fact, adapt everything and using this second step and this first step, in fact, combine everything in order to show the existence of this function in this first statement, okay? So we can conclude the tree decomposition of bounded adhesion case. And the fourth step is what I told you. It consists of dealing with graphs which are almost embeddable in surface. So whenever you have all of these four steps, you use Robesson-Sumor structure theorem, and you can conclude. Okay, that's the rough idea. So now let's zoom a little bit more, especially on the first and the third step. I think it's the most interesting to zoom in. So the first one, I told you that in the first step, what we do is that we prove some weak conditions that allows to deal with tree decomposition of bounded adhesion. So this tree decomposition, we can express them in terms of notion of capturing. So for a family of paths to capture the adhesion of a tree decomposition. So let me explain it a little bit. So here's the formal definition. I'll try to give you a picture on the blackboard, or at least to give you some intuition. So assume you have a graph, a tree decomposition, right? So this tree decomposition has bounded adhesion. So this means every adhesion set here, so intersection of two bags, it's bounded, it's at most k, okay? And assume moreover that we knew how to prove already in previous step that every torso or every bag has bounded basis number, right? So everyone has bounded basis number. And we would like to inherit property of bounded basis number for the whole graph, to show that the whole graph also has bounded basis number. And very simple condition in which, a very simple case, but weak one, in which we can conclude is whenever there exists a family of paths. So this family, it could be a multiset of paths. There could be the same path appearing many times. It matters in our proof, in fact. Of paths in my graph between every two pairs of adhesions. And it's not only between every two pairs of adhesion, it's in fact every two pair of vertices whenever they appear in one adhesion, but maybe it could be that they appear also a second time in this adhesion. And then I should also be able to define a path between them, second one. So whenever there are two paths that appear for each pair of paths and every adhesion that contains them, I should be able to find a path. So this path is not, we don't have any condition on where it is contained. It could be something like this. But if whenever, and here it appears somewhere else, so there should be a second path, which could be the same. That's what it is, the multifamily, right? A multiset. And what I mean by capturing adhesions is really the following. So I will say that a set of paths, so my blue set of paths P, I will say that it captures the adhesion if there is such a path for every two pair of vertices and every adhesion that contains them, right? So I take every two vertices. If there is an adhesion that contains them, an adhesion set that contains them, then there is a path in my family, so this PUVA that connects them, okay? And it's any path in my graph. It could travel everywhere in my graph. And the case in which we are super happy is, in fact, whenever someone gives me a tree decomposition with bounded adhesion, every part has bounded basis number, and if moreover you give me a path system like this, so a set of paths that captures all adhesion, all pair of vertices belonging to the same adhesion, with respect to this definition that I just gave, and so that moreover, the congestion of this path system, the edge congestion, exactly the same way that I defined it before, right? So every edge appears in a bounded number of paths. And this bounded is always up to counting many times the same path if there is the same type multiple times, right? So if we have a bond, a universal bond on the congestion of such a path system, and you give me this, then it's not hard to conclude. It's not hard at all to conclude. Yeah. That's what I wanted to say, but just something. No, okay. Yeah, so then you can conclude. Okay, and so I will not expand on the proof. The only thing that I would like to say on the proof is that it does not depend on any machinery. It's quite a natural proof. It's a couple of pages, and it's really, if you're given this condition and you try to prove the theorem, it really corresponds to whatever you can do without using so much fancy stuff. Like it's really like, yeah, you use the definition of basis number, you use definition of 3D composition, of capturing, of path systems that captures adhesion, and it's really quite a natural proof. There's no very new big ideas in this proof. The only thing that I'd like to say is that, yes, so it's very weak. And why is it very weak? Because already, if you look at cycle, a long cycle, and if you look at any 3D composition, so we know that cycle, it's very easy to see that 3D composition of cycle. Cycles, they have 3 widths too. So there exists a 3D composition where each bag has size 3. But the problem, if you look at every such decomposition, 3D composition of a cycle, where bags have size at most 3, they will never admit such a path system, right? It's impossible with bounded condition because, like, for example, there should be some bag such that on both sides there are two long pieces of path, and in fact you have to capture these people, right, in the adhesion, so the people which are there, for example. And if you start doing this, then you will need also a path like this, and you will obtain a lot of paths that contains the same edge which is there. So long cycles, they do not admit at all, they do not satisfy the theorem. So already the theorem, you cannot use it whenever you consider like 3D composition of bounded widths of cycles. So that's why I say it's very weak. Okay, but the nice thing with cycles is that in fact, all 3D composition of bounded widths of a cycle, they are path decompositions. And that's what motivates really this second step. So in fact, this second step consists of dealing exactly what I told you with path decompositions. So that for cycles, that's exactly, if you take our proof in a stupid way and you try to make it work, so that's exactly the way we will do it for cycle to bound its basis number. Okay, so I already told you about this. So yeah, our initial proof for this step 2, it relied on Schimon's forest factorization theorem. And so we obtained the following bound. And in fact, yeah, so here is a more precise statement of the result of Miraftab, MacLane, and Uditsky. So here is the polynomial bound that they could obtain, which is obviously far better than ours, and which doesn't use any semi-group theory factorization theorem. So yeah, maybe let me ask, how much time do I have now?
We talk for 45 minutes.
Oh, okay, I was quicker than expected. Okay. Okay, so I can slow down a little bit on the third step then. Maybe let me just mention that, yes, so in fact, initially, yes, so this group of people, they were interested, in fact, of the main result, it's a bound, a linear bound on the path width of a graph, okay? So if you have a graph, if you look at graphs with path width at most k, they proved, in fact, that they have basis number at most 4k, and they were trying to find some optimized bound for the basis number, polynomial ones, quadratic, in fact, for the basis number of graphs with bounded 3 widths. But it seems like the methods, they could not adapt them, right, for the general 3 widths case. But the method, they were powerful enough, in fact, to derive this bound for more general path decompositions, right? Okay, so now, yeah, let me talk about the third step. So third step is really like to deal now with general 3D composition with bounded adhesion, and to prove so this general statement that we already saw before. And yeah, I told you, so yeah, maybe let's start focusing on the bounded 3 widths case, because in this bounded 3 widths case, so in fact we can already immediately conclude with a very simple polynomial bound on the basis number of graphs with bounded 3 widths. And by just using the result, the work of Bojancek and Filipchuk, and it already gives kind of all the intuition of what's going next. So I will spend more time on this one. So yeah, so a key lemma that they proved, Nikolai Bojancek and Michał Filipchuk in their work, is that if you look at graphs, so yeah, here I have a picture, yeah, with bounded 3 widths, so that admits a 3D composition where every bag, every piece, it's small, right? Then what you can do, either it's a path decomposition, or if it's not a path decomposition, this thing, in fact, what you can do is that you can quotient it. So what do we mean by quotient it? I mean, you can partition your set of nodes in the tree into subtrees, right? So connected subtrees, so this red set. So that now, if you look at the 3D composition that you obtain when merging, so by merging I mean doing the union of every bags in every subtree, right, in my collection, in my partition, you now obtain a 3D composition that admits this time a family of paths that captures the adhesion. And what's the cost that you paid. So yeah, this family of paths, it has bounded edge congestion. In fact, it's even polynomial. It is k4, k to the 4. And so that moreover, so there is something that you paid, of course, because we merged things, but the things that we merged, they still have a nice structure, and by this I mean they admit the path decomposition, they have bounded path width, so they admit the path decomposition, so maybe not anymore of width k, but up to some constant, so of width at most 3k plus 1, right? And yeah, and again, so yeah, well, you can see that when you merge this, the addition sets, so the new addition set that you have, they were also addition set of the previous decomposition, right? So it doesn't change also the addition of my tree decomposition, so it preserves the property of addition k, okay? So this is a rough statement. So maybe it's impossible in general because of this very long cycle to find some tree decomposition and some path systems, yeah?
What does it mean that the family of paths captures the path region?
I was too quick. That's exactly what we defined in step 1. So it's exactly the thing we are happy. So there is one single thing you're super happy with, is whenever you can find a family of paths that captures the addition. So that means that for every 2 people that belong in a common addition, you can find a path between them. And you take a set of paths like this, such that for every 2 people that belong to a common addition, you can find a path that connects them. And whenever you can find such a path system or a family of paths that captures all the additions, so every pair of people that belongs to the same addition, plus if you can moreover ensure that this family of paths has bounded congestion, edge congestion, so by this I mean that every edge in my graph appears in at most a bounded number of people in my path system, in my family of paths, then we can conclude. This was our first step. But thanks for asking. And in general, so that was what I was trying to explain, so maybe it was not super clear. For long cycles, if you look at, if you take a very long cycle, and if you look at tree decomposition with bounded widths of long cycle, you will never be able to find such a family with bounded edge congestion, right? Every family that you can find of paths in your original graph that captures all the additions, they will always have unbounded congestion, right? There will always be at least one edge that appears in many numbers. But the thing, what they proved, in fact, and that's what's really magic, is that, yeah, so their hypothesis, like this thing, okay, they didn't phrase it this way, you have to work a little bit from that work, in fact, to derive this statement, but it can, when you have the work and their lemmas, it's a little bit of work to get this statement, but it's more or less what they prove, really. It's the core idea, is that, okay, maybe it's not true that in general you can find a family of paths that captures the addition and has bounded edge congestion, but in fact, up to doing something, and this thing is really quotienting some tree decomposition. If you start from a graph with bounded widths, with bounded tree widths, so from any tree decomposition with bounded widths at most k, you can always find another tree decomposition up to quotienting, so to merging like this, right? So you find some set of subtrees, you do the union, you merge all of the bags, right? So to obtain this red tree decomposition, and up to doing this now, you obtain a new tree decomposition, now with this property that we like a lot from first step, that there exists, it admits a family of paths that captures all the additions and which moreover has bounded edge congestion. And what you paid, of course, is that maybe, so now your tree decomposition does not have bounded widths anymore, but still you have some structure, and by structure I mean that everything into each bag, in every bag, admits as bounded path widths, right? So admits a path decomposition with bound widths at most 3k plus 1.
So these adhesions in the new tree decomposition, they were, if you do it like this, they are adhesions in the old one. So
yeah.
So in fact, you're looking for edges where you have these paths, and then if you don't, then you somewhat contract. Yeah, and that's probably what they do in the proof.
It's okay. Let me say that what they do, it's quite technical. Like what they do, it's really some. Okay, so if you want to do it more formally, it's 2 steps in the proof. I can give you a little bit of intuition of the proof, but the goal is really, so the first thing, if you want to prove this, and that's why I drew this result in fact this way, the first idea is to look at your tree decomposition as rooted. You take a root, and now you try iteratively to find, okay, which will be your red set that you can find, right? And that contains it. And there are 2 cases. Either there's already a path system that you're happy in some inductive hypothesis that will capture and have low congestion between 2 things, or if there's not, it means that in fact there's some kind of Menger, so that means that if you have 2 vertices here, and the only way to connect them is to go through the same addition. And in this way, they will then add this thing into the family, and then they will keep going on. And with a nice inductive hypothesis, in fact, what they will try to do is to say, okay, I look at the previous adhesion, what I had so far, and my question is, are there two people that I can connect by just staying here, or do I have to go further? And if I go further, then that means that this will be a candidate to add it in my above potato, but it's tricky to do it formally. It's technical proof. But the rough idea is really this, is to take something, to kind of merge it, and then to say, okay, is this thing, this adhesion below, does it give the separator between U and V? If it gives a separator, then we can play with it, and in fact, this will give me a candidate for a path decomposition of what I'm constructing so far. But if it's not, that means that, yeah, maybe in fact I can find two paths differently, and I can use them to construct such a family of paths.
So if there is a separator, you merge it, and the separator will help you to build up the composition, and
exactly.
If there is no separator, then you should have your paths.
And if there are
an adhesion in the outcome.
And if there are many separators, in fact, one of the things is that they should appear in some other way, in some kind of Menger theorem that allows to do it, right? So if you choose to go there and do some path decomposition, then when you go back, you will keep going on with the path decomposition like this. So really, this path decomposition, it will follow the order that you're given when routing. So it's really the kind of general idea. But there are at least two big ideas. One which is to find the correct induction hypothesis, which is super magic. Like you can read it, and it's only after the 5 readings that you really understand why this induction hypothesis works and are the correct. It's a very nice trick. This is the one that allows them to get this polynomial. And the second trick is to try to use Menger in some nice way and to make this work. But I can tell you more later if you want. Okay, so let me just tell you that, so in fact, once we have this result, once we have this result, in fact, by combining already with everything that we saw before, we can already get an answer for graphs with bounded tree-widths, right? We just combine it with our result from step 1. From step 2, we saw that having bounded path widths, we already know how to conclude with how to bond the basis number of graph with bounded path widths. So as a corollary, you can get already immediately with everything that we saw so far that every graph with bounded tree widths has bounded basis number. And if moreover you use this linear bond that we just saw of 4k for the basis number of graph with path width k, you can get the following polynomial with a bond on the basis number of graphs with bounded tree widths. And I think, so this k5, I don't believe it to be optimal if you want to try to optimize this way. I wonder if they didn't, I don't know, the paper is fresh. I think that they conjecture that it should be k. That will, so there is some work. Okay, and now, so if we really care, so if we go back to our big proof framework and we want to now get our general result for 3D composition of bounded adhesion, so the thing that we did, in fact, is to try to find some analog, some good analog statement of this result of Bojanczyk and Filipczuk. And in fact, it's possible, again. It's possible. So now the thing that you will have is, if you are given a 3D composition, that's what I mean, of bounded adhesion, what you can do again is that you can maybe quotient it again. And at the end, so whenever you finish quotienting it, you can find again a family of paths that we are super happy with. So by this I mean which captures all the adhesions and which have bounded edge congestion. So again, it's the same edge congestion, it's the same trick for this part of the proof. And now, you started from any kind of graph, any kind of 3D composition. So maybe it's not true anymore that you have bounded path widths, but what we prove is that in fact, still your 3D composition, you can have some path decomposition of bounded adhesion. So now it will be 3k. It's not k anymore. And whose torso, they are almost subgraphs. They are almost all subgraphs of graphs of my initial decomposition. And it's up to adding some apices. So this plus 2k, it means adding 2k apices. So that's, I don't want you to really understand the statement, but that's the key thing is that the key message is that this result, this work of Bojanczyk and Filipczuk, the result that is the tool that they introduced, we can in fact adapt the proof up to some work, but there are not really fundamentally new ideas to get the following result for general 3D compositions, following structural theorem for general 3D composition of bounded adhesion. And so using this now, we can prove the following bond. So this following bond, it's again, if you use, instead of our original bond, which came from Szymon's factorization, you can get this b plus k log square k that was given by Miraftab, MacLane, and Uditsky work. And so that's more or less a rough idea of how we deal with 3D composition. And yeah, maybe let me mention that there is a key thing in this generalization is that we needed, in fact, whenever generalizing this step, we needed this monotone. And that's quite annoying because for some time we thought that we could replace this monotone by hereditary, and that's not clear yet. Like if we, in our general statement for this hereditary of basis number property, whenever considering 3D composition of bonded adhesion, if we can replace this monotonicity by hereditary, and it's not clear yet. Like it's still something that we, for quite a long time, and we thought that we could replace this monotone by hereditary. It's not really the case, and yeah, and the reason, of course, is that yeah, we do some job at some point. We have to consider torso, and the fact that you consider torso is really the real reason. But yeah, that's just a side remark. But yeah, so that's really why you pay this monotone in our proof in this part. Okay, that's more or less all I wanted to say, if I want to keep you alive about this step. And now, yeah, the fourth step, so it's the last one I told you, yeah, there is this almost embeddability result, so graphs which are almost embeddable in bonded surface, in the surface of bonded genus. They do have bonded basis number, so this is more technical than what we expected, but the rough idea is that, yeah, so if you have some disk separating, some cycle that separate your vortices that you had, so the apices are super easy, as we already discussed, to deal with, right? So you can just consider a graph, try to consider a graph and bound its basis number whenever you know that it's a graph embedded in the surface of bonded genus, plus some vortices that you have. And whenever these vortices, you glue them, and the separation to glue them, like the boundary of this disk, you glue them to, it's a cycle. In fact, it's very easy to conclude. But the real problem is whenever this boundary is not a cycle anymore, and it's really for this, because of this non-monotone behavior. Not behavior of the basis number. And yeah, let me say that yeah, in order to deal with this technical issue, we need to use some results from Epstein, also from Mazwa, and one of these results, one of the key results that we need to use, is we need to pay, we use the fact that we already are happy with the bonded Tree-Width case, and yeah, as a step we use the fact that yeah, so every graph which is embeddable in surface of bonded genus, it also has, and moreover, if it's dual, as bonded diameter, then you can conclude that this Tree-Width is bonded. So that's some kind of extension of the property that outer planar graphs, they have bonded Tree-Width, they have Tree-Width too, right? That's a rough generalization. But yeah, let me just, I would like not to enter into details into this part. So yeah, so let me maybe conclude. So yeah, so here's a reminder of our main result. So here's the constant that we have. So first obvious question that we could have is, okay, can we have some significant improvement? So I don't believe that replacing this 10 by a 9 would be very interesting in its own, but I believe that maybe already trying to find some polynomial here of some correct degree, right, decent degree, it should be something interesting. So yeah, I don't have any idea. We don't have any examples so far of something, in fact, that would not of some better lower bound than something in polylog G, log of the size of H. So it might be that in fact this polynomial bound, it's not even a polynomial, the best one. Maybe it might be a log square, because everything that we saw so far, it was log square the best bound, right? We have no idea, but the thing which is quite clear is that if you want to do improvement on this bound, and to find maybe the right or some closer to optimal bounds, the thing that we should do is maybe try avoiding a Robertson-Seymour structure theorem. That's something. Okay, so yeah, natural case is okay. In which direction can we try to extend, right? So what kind of parameters, for example, what kind of more general class than the class which have bounded, which excludes some graph, some fixed graph as minor, have bounded basis numbers. So some candidate for which we have no answer is click width. So is it true that if a graph has bounded click width, then it has bounded basis number? It might be. Like already clicks, they have basis number at most 3. Biclicks also. Co-graphs, I think they do have also. Let me just say that it's wrong if you replace by twin widths. The reason is simple. If you take, I told you about this large girth, it's not because of the girth. You take, okay, it's kind of because of the girth, but okay, the thing is that you take any graph, and there is some property of twin widths, which is that if you subdivide roughly log n times all its edges, then it will have twin widths at most any constant, like 4. Right, that's a general property. So it's really twin widths. It's not closed, like it's not like non-decreasing under subdividing edges. But basis number is. We just saw that subdividing edges doesn't affect the basis number. So that really make it fail very easily for twin widths. But click widths, we don't have any idea for now. Yeah, let me also mention that topological minor, it doesn't work because we have family, in fact, of cubic graphs we cannot replace excluding a minor by excluding a topological minor or having bounded degree, because we have cubic graph with very large basis number, because the construction I mentioned before. Okay, so yeah, there was this question I just told you. Can we, in our general results on 3D composition of bounded adhesion, can we replace this monotone by hereditary? That will already allow us to consider some larger class, because we could have some torso which are cliques, bicliques, this kind of thing, co-graphs, I don't know. And, yeah, and the last question that I like a lot is that, in fact, I think that this question doesn't make sense on infinite graphs. So by this, let me give you a small motivation, very nice result that we have. There exists MacLane's planarity criterion on infinite graphs. So if you take infinite graphs, so you can define cycle basis exactly as before. So you just take the finite cycles and you look at whatever they generate, right? And in fact, so yeah, so if you look at this notion, you can again define basis number. And Kirsten Thomassen, he proved that, in fact, graphs with basis number at most 2, so the infinite one, he gave a characterization, a MacLane's planarity criterion. He proved that they are exactly the graphs that are planar, plus they should admit a planar embedding with no accumulation point. So what does it mean? It means that there is no point in the plane with an infinite sequence of vertices closer and closer and closer, right? Take the infinite grid, or the tree, right? These have no accumulation point. So, and this is easy to see that they have basis number 2. But if you take some graph which has not this property, for example, is the infinite, you take the cylinder, the Bay infinite cylinder, and you take a grid, right, drawn on it. And whatever drawing that we will do, it will look like this, right? You will go infinitely outside, infinitely inside, right? So that's something like this, right? So everything like this, it will induce some accumulation points, right, which is hidden somewhere there. And this has not basis number 2, and the easy reason, at least to see that it has not, is that not only you need to generate these facial cycles, right? So you could take the facial cycle, for example, but you must also add at least one of these cycles, right? Like this, which is like this, like one of these slice cycle. So there is a version, and yeah, a question. So I don't know at all if it's true or wrong. I expect it to be true, to be wrong. Maybe we don't know enough about infinite graphs. But some very natural question is, okay, is it true that planar infinite graph has bounded basis number? Minor-excluded infinite graphs. So let me just mention that it's true whenever you look at Cayley graphs, because we know that they are finitely presented for those who know about finite presentations. But for general infinite graphs, we don't know. Yeah, I think that's all I wanted to say.